All right. We are talking about electric potential difference today, and before we do that, I want to remind you guys that you already have a personal experience with this that you're familiar with and makes sense to your brain, so that we can apply it to this sort of situation. This is the surface of the Earth. Okay. If you take an object I totally used the wrong pen for that. There we go. Okay. And you hold, you take a ball. Okay. And then you raise it up in the air. That high, above the ground. What have you given the ball? The ball has what when it is above the ground? Mm-hmm. It has potential energy, right? Okay, here's a hint. Okay. It has potential energy when it's above the ground. Okay, and the further away that we move, the more potential energy it gets, right? Not only that, but if this ball was more, if we increase the mass of the ball, it would increase the potential energy, right? So things Okay, so things that would affect the potential energy would be the height or the distance. Okay, and the mass of the object. What's that? Effect. So the things that affect potential energy are the distance above the Earth and the mass of the ball itself. Now, there are some other things that affect it, but as long as we're staying close to the Earth, then... What's that? NRG. Okay, but as long as we're close to the Earth, then these are really the only two things that are affected, because there are other things that are constant. Okay? The mass of the Earth is constant. Okay? The radius of the Earth is constant. And if we're going to get out into space, then we're really talking about way out, gravity. Then we have to change our equation a little bit, and we get into the universal law of gravitation. So if we do that, okay, and here's your massive ball. Okay, and it changes in potential energy. It goes from here to here, right? It gets further away, means it increases in potential energy, right? Okay, we're just a heck of a lot further away than just right and lifting it up off the Earth. We're moving it a significant distance away. The idea remains the same. Okay, and we can calculate our potential energy, which are U. Okay, or let's call it PE for right now, or PE. Potential energy here and our potential energy here, okay, it's going to change. So our change in potential energy, okay, we'll call this at R1 and R2. So our change in potential energy here would be this amount, our PE at R2, minus our PE at R1. It's our final minus our initial, right? Okay. What do you call when you subtract something? What is the result when you subtract something? What's that? What do you call the answer when you... Okay, you call it the difference, right? So... what we find here, this right here, this change in potential energy, is the potential energy difference between the two places. Yeah? Does that make sense to you guys? Okay. The reason this has a change in potential The reason this has a change in potential is because Earth has a gravitational field around it. And no matter where we are, it's always pointing towards the center of the Earth. But if we're on the ground, if we're real close to the center of the Earth, it seems like we're pointing in what direction? Down. So the gravitational field close to the Earth is all pointing down, essentially, because we're essentially flat. The Earth isn't really flat, but as far as we can tell, for all intents and purposes, it's flat enough to consider it flat, and all these lines aren't going to change their direction. Okay, they're all going to be pointing down. And so if we lift a massive object against gravity, we're giving it a potential difference, right? We've changed its potential. Okay, the same sort of thing applies in electricity. I'm going to trip you out here a little bit. Because instead of, it's going to be plus, 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 minus, and minus. Tyler. Oh, never mind. Okay. Oh, you can't see that, can you? Okay. So, if this is our electric field, okay, now imagine that these go really long. These go in both directions, right? So we just have these really long plates of charge, right? We have a positive charge, a length positive charge here, and a length of negative charge over here. Our field is going to look like our field is going to go in one direction, right? Okay. So if our field's all going in one direction, well, hold on to this for a sec. Sorry, let's come back up here. What does it require for us to move this ball from here to here? Yeah, it requires a force for us to move this ball, right? We have to lift against the pull of gravity to get it up this distance. And there's actually work that we have to do, and the work that we do equals the change of potential energy, but to do the work, it's force over distance. Yeah? Is this ringing a bell from you guys from last semester? Okay. Well, if we're going to, and this is, mind you, this is against the direction of the field, right? So if the field is pointing down, to lift it up against the field, we would have to do force. Yeah? Okay. So, if we have a positive test charge right there, what would have to happen to get it to move to there? We would have to do what? We would have to do force, okay, times the distance. So we would do work on the charge, right? Okay. Now, what things could affect the amount of work we do on the charge? Now that we're talking electricity, what could affect the work that we have to do? Okay, the amount of distance, right? Okay. What if this had a lot of charge on it compared to a small charge? Would that change the amount of work we have to do? Yeah. Yeah, if this is a big positive charge and here's our positive field going in that direction, we would have more work to do because the charge would be more. Okay. If the field was stronger, okay, we would have to do more work. So imagine more gravity. We have to lift the ball against more gravity. We would have to do more work, right? Okay. So what we're finding here is if we move this ball, or this little charge, this distance, okay, and we're doing more work, and then we hold it here, what have we given this charge? We've done work on the charge to move from here to here, and we hold it there. What if I let go of it? What would happen to it? What's that? Where? Remember what the lines mean. Remember, the lines are the direction of the force that a charge would travel if it was in that spot. So if we let go of this thing right here, it would accelerate that direction. Yeah? Okay. So if we push it this way, and I hold it here, all of a sudden it has what? Leah? It has potential energy. Okay, but now, so compare it to, what if I do that, and all of a sudden, this is the ground, and these lines are gravitational field, right? So now if we lift it up here, then it would be lifting up against gravity, and so if we let go of it, it would fall to the ground if this is the ground. Well, now we have a different kind of field. Okay, we now have an electric field, and it's going to go this way instead. So electric fields can point in any direction. So this, what we've done here is we have created electric potential difference. Okay, and this is measured in joules per coulomb. C-O-U-L-O-M-B. Darn it.
It's okay, we know what you do extra.
C-O-U-L-O-M-B. Okay, or a joule per coulomb, which equals 1 joule per coulomb equals 1 volt. And we'll stop there, and this should be enough to get you guys started on your homework. On your homework.